Space is infinite. We are surrounded by a never-ending sea of planets, stars, and galaxies that extend outward in every direction for a distance so vast, so incomprehensible, that the human mind simply cannot hold it. That is what we are told, at least. That is what the science says. But here's the thing. When you actually look up at the night sky, when you step outside on a clear night and stare into the darkness above you, you don't see an endless glow of light stretching into eternity. You don't see the infinite universe you were promised. What you see instead, in that deep black expanse beyond the stars, is nothing. Pure, absolute darkness. A void. And that void is telling you something important. That blackness is not just empty space. It marks an edge. Not the edge of the universe itself, we'll come back to that, but the edge of our ability to perceive it. The furthest point that human observation, in any form, has ever been able to reach. The distance from where you are sitting right now to that edge, the boundary of what we call the observable universe, is approximately 46.5 billion light-years. And that boundary extends outward in every direction equally, forming a perfect sphere of observable space around us, roughly 93 billion light-years across. Now, a light-year is simply the distance that light travels in 1 year, and light moves through space at a constant speed, roughly 186,000 miles per second. Nothing in the known universe can move through space faster than light. That is not a suggestion. That is a fundamental rule, baked into the very structure of reality. So, when physicists and astronomers measure distances across the cosmos, they use light travel time as their unit of measurement. And for our observable bubble, the number is 93 billion light-years from one side to the other. Everything you have ever known, every planet, every star, every galaxy ever discovered, every image ever captured by a space telescope, every signal ever received from the cosmos exists within that sphere. Everything, every single thing our civilization has ever detected or studied came from inside that bubble. And here is the part that should stop you cold. We are at the center of it. Not because the universe revolves around us, not because we are special, but because we are the observer. The bubble is defined by what we can see, and we are the ones doing the seeing. No matter where you stand in the universe, your observable bubble is centered on you. We are each, individually, the center of our own perceivable universe. Think about that for a moment. Now, here is where things start to get genuinely strange. The edge of that bubble, the boundary where our perception ends, is not actually black at all. If you could somehow see beyond the visible spectrum of light, beyond the range that human eyes are capable of detecting, you would find something extraordinary waiting for you at that edge. A wall of light. Ancient light. The oldest light in the entire history of the universe. This is the light that emerged from the very beginning of everything. From the event that most people know as the Big Bang. And right away, we need to address something. Because the term Big Bang is one of the most misleading phrases in all of science. It suggests an explosion, a single dramatic detonation at a fixed point in space, throwing matter outward in all directions like a grenade going off. That mental image is intuitive. It's easy to picture. And it is almost entirely wrong. We'll get to what actually happened in a little while. But for now, the important thing is this. At the very outer edge of our perceivable universe, there exists the first light that the universe ever produced. And the reason we can't see it with our naked eyes comes down to something fundamental about the nature of light itself. Picture light as a wave, not a particle, not a beam, a wave. Like the ripples that spread across the surface of a pond when you drop a stone into the water. Right at the point of impact, those waves are tight, compressed, clearly defined. But as they travel outward, they stretch, they spread. The peaks get lower, the distance between them grows, and eventually, at some point, far enough from the center, those waves become too faint, too stretched out, for the human eye to detect. You can no longer see them, but that doesn't mean they've stopped. The energy is still there. The wave is still moving. It's just moved outside the range of what your senses can measure. That is exactly what happens to light as it travels across the universe. Light exists along a spectrum. The part of that spectrum that human eyes can detect is called, appropriately enough, the visible spectrum, a narrow band of wavelengths that we perceive as colors, from deep violet on one end to deep red on the other. But the spectrum extends far beyond what we can see. On one side, beyond violet, you have ultraviolet, then X-rays, then gamma rays. On the other side, beyond red, you have infrared longer wavelengths, lower energy, invisible to the human eye. As light travels across enormous distances of space, it gets stretched, the waves elongate. And when that stretching pushes the light beyond the red end of the visible spectrum and into infrared, our eyes can no longer pick it up. The light is still there. It hasn't disappeared. It's just become invisible to us. This is why, when you look up at the night sky, you see black. The light from the oldest, most distant reaches of the universe is still arriving at your eyes every single second. But it has been stretched so far into the infrared that you simply cannot perceive it. This is also why we build instruments like the James Webb Space Telescope. The James Webb can see deep into the infrared spectrum, far deeper than any instrument we've ever launched into space before it. Where the human eye sees nothing but darkness, Webb sees light. Ancient, stretched, profoundly faint light from objects that formed in the very early universe galaxies that came together just a few 100 million years after the Big Bang. Through the eyes of James Webb, the blackness of space opens up into a staggering tapestry of early cosmic structure that is almost impossible to comprehend. But even James Webb has limits. Even the most powerful space telescope humanity has ever constructed cannot see all the way to the edge. At a certain distance, even Webb's infrared capability runs out. The light becomes too ancient, too stretched, for even our best instruments to resolve into images. The black void remains. So then, a reasonable question. If we can't see the edge, not with our eyes, not with night vision goggles, not even with the most advanced space telescope ever built, then how do we know there's light out there at all? How do we know there's anything at the boundary of our observable bubble? This is where it gets fascinating. We have to go deeper, deeper than infrared, deeper than anything you might typically associate with the word light. We have to go all the way down to microwaves. Right now, at this very moment, you are being bathed in microwaves. Not from an appliance from the universe itself, from every direction simultaneously, a faint and entirely invisible microwave signal is passing through you, through the room you are in, through the Earth, arriving from the most distant corners of observable space. It is so weak that you cannot feel it, so stretched that no human sense could ever detect it. But it is there, and we can measure it. Hidden inside that microwave signal is something that may be the single most important discovery in the history of cosmology. It is called the Cosmic Microwave Background, or CMB, and it is the direct afterglow, the still traveling remnant of the first light the universe ever produced. The light from the very beginning of time, now so ancient and so stretched that it has crossed far beyond the visible spectrum, far beyond infrared, and arrived at us as the faintest possible whisper of a microwave. We can map it. We can measure the tiny variations in its temperature across the sky. And when we do, what we see is something stunning. The universe is not, and never was, perfectly uniform. There are patches of slightly higher density and slightly lower density distributed across the sky in a pattern that mirrors almost perfectly the distribution of galaxies and cosmic structures we observe today. The seeds of everything that exists were already present in that first light. The age of the CMB, the age of the oldest light we can measure, is approximately 13.8 billion years. That is how old the universe is. That is when the first light emerged. But here is the problem. The distance to the edge of our observable universe, the distance to that ancient light, is 46.5 billion light years. Read that again. The light is 13.8 billion years old, but it is 46.5 billion light years away. If light travels at a constant speed and nothing moves faster than light, then how does 13.8 billion year old light end up 46.5 billion light years away from where it started? That is not a small discrepancy. That is not a rounding error. That is a gap of more than 30 billion light years between where physics says the light should be and where it actually is. And the answer to that question, the real answer, requires us to go back to the early 20th century, to a man who had already changed the way we understand reality and examined the one thing he was absolutely certain about that turned out to be completely wrong. To understand how the universe can be older than it is wide, we need to go back to the early 20th century. We need to go back to Albert Einstein, and we need to talk about the biggest mistake he ever made. Because it turns out, hidden inside that mistake was one of the most profound truths about the nature of the cosmos. Einstein was working on what would become his masterpiece, a framework he called general relativity. This was not just another scientific paper. This was an attempt to write the operating manual for the universe. General relativity described the relationship between space and time. It explained how gravity works, not as a pulling force between two objects, as Newton had described it, but as a curvature in the fabric of space itself, caused by the presence of mass. It established the speed of light as an absolute cosmic speed limit, and it did all of this with a mathematical elegance that stunned the scientific world. But when Einstein tried to apply his own theory to the universe as a whole, to ask what general relativity said about the structure and behavior of the cosmos, he ran into a problem. His equations kept producing a universe that was not sitting still. They kept producing a universe that was either expanding or contracting. The math would not allow for a universe that simply existed in a stable, unchanging state, and that deeply bothered him, because the assumption at the time shared not just by Einstein, but by the overwhelming majority of the scientific community, was that the universe was static, fixed, eternal, a vast and uniform sea of stars that had always existed more or less as it appeared, and would continue to exist in more or less the same configuration forever. The idea that the universe might be changing, growing, evolving, moving, was not a mainstream scientific position. It was, frankly, not something most serious thinkers had even entertained. So Einstein did something that, in hindsight, feels almost painfully human. He didn't trust the math. He didn't follow his own equations to their logical conclusion. Instead, he introduced a correction, a new term he inserted into his field equations, specifically to make the math behave the way he expected the universe to behave. He called it the cosmological constant. What the cosmological constant represented, physically, was a kind of repulsive energy, a pressure built into the fabric of space itself, pushing outward against the inward pull of gravity. A cosmic anti-gravity. Einstein set the value of this constant so that it precisely balanced the attractive force of gravity across the universe, producing the static, unchanging cosmos he believed in. He was wrong about the static universe, completely and demonstrably wrong, as we will see in a moment. But the cosmological constant itself, the idea that empty space contains an inherent outward pressure, a repulsive energy woven into the vacuum, turned out to be one of the most important ideas in the history of physics. Einstein had stumbled onto something real. He just didn't know it yet. He actually later referred to the cosmological constant as the greatest blunder of his career. But in one of science's great ironies, the blunder was not inventing the constant. The blunder was abandoning it. Now, While Einstein was wrestling with the shape of the universe from a theoretical direction, an astronomer in California was about to demolish the static universe from an observational one. His name was Edwin Hubble. Today, Hubble's name is attached to one of the most famous telescopes ever built. And that is entirely appropriate because the discoveries Edwin Hubble made in the 1920s rank among the most transformative in the history of astronomy. He didn't just refine our understanding of the universe, he fundamentally restructured it. To understand what Hubble did, you have to understand what astronomers thought they were looking at before he came along. At the time, the prevailing assumption was that every point of light in the night sky was a star, and that all of those stars belonged to a single system, the Milky Way. Our galaxy, in other words, was not just one galaxy among many. It was understood to be the entirety of the visible universe. Everything that existed, everything that could be seen, was part of one single sprawling structure of stars. There were, however, some puzzling objects in the sky that didn't quite fit that picture. Scattered among the stars were these faint, diffuse, smudgy patches of light too spread out to be individual stars, too bright to be easily dismissed. Astronomers had cataloged them and given them a name, nebulae, from the Latin word for cloud. The assumption was that these were simply large clouds of gas and dust, drifting between the stars within our own galaxy, unresolved, unstructured, and not particularly mysterious. The largest and brightest of these objects was a nebula called Andromeda. Edwin Hubble decided to figure out exactly how far away it was. To do that, he needed a measuring stick, some reliable way to calculate distance in space, and he found one hidden inside the nebula itself, in the form of a very particular type of star called a Cepheid variable. These stars have a remarkable property. They pulse. They cycle from bright to dim and back again in a regular, repeating rhythm. And crucially, the speed of that pulsing is directly linked to the actual luminosity of the star, the true brightness it is emitting, regardless of how far away it is. The slower the pulse, the intrinsically brighter the star. This relationship is consistent and predictable, which means that if you can measure the pulse of a Cepheid variable, you can calculate how bright it actually is, and then, by comparing that true brightness to how bright it appears through your telescope, you can work out exactly how far away it must be. Hubble found a Cepheid variable inside the Andromeda Nebula. He measured its pulse. He calculated its true brightness. And then he compared that to what he was actually seeing through his telescope, which was a star that appeared extraordinarily faint. The conclusion was unavoidable. For a star that bright to appear that dim, it had to be at a distance that placed it far beyond the outer edges of our own galaxy. Andromeda was not a cloud of gas floating between nearby stars. It was an entirely separate system, a vast collection of hundreds of billions of stars, located so far away that the entire thing appeared as nothing more than a faint smudge in the sky. Andromeda was another galaxy. And if Andromeda was a galaxy, then the universe was not a single structure. It was a collection of them enormous islands of stars, separated from each other by incomprehensible distances of empty space. The scale of everything we thought we understood expanded, almost overnight, by a factor that is difficult to even quantify. That alone would have been enough to cement Hubble's legacy, but he wasn't finished. Hubble had a colleague, an astronomer named Vesto Slipher, who had spent years carefully studying the light coming from these nebulae, these galaxies. And Slipher had noticed something deeply strange. In almost every case, the light from these objects was shifted, not changed in intensity, not distorted, shifted, specifically shifted toward the red end of the spectrum, toward longer wavelengths, toward infrared. We talked in the last chapter about how light behaves like a wave, and how those waves stretch as they travel across vast distances of space, eventually moving out of the visible spectrum and into infrared. But what Slipher was observing was different. This wasn't just the passive stretching of ancient light. This shift was a signature of motion. It's called the Doppler effect. You have experienced the Doppler effect your entire life without necessarily knowing what to call it. Think about the last time an ambulance drove past you on the street. As it approached, the siren had a higher pitch, tight, compressed, urgent. And then, as it passed and began moving away from you, the pitch dropped lower, more drawn out, fading. The siren itself didn't change. The ambulance wasn't adjusting the sound it was producing. What changed was the relationship between the source of the sound and the person receiving it. When the ambulance is moving toward you, each pulse of sound it emits is physically closer to the previous one by the time it reaches your ears, because the vehicle is moving in the same direction as the sound. This compresses the waves, which raises the pitch. When the ambulance moves away, each pulse has to travel a little further than the last before it reaches you, because the vehicle is retreating from you while the sound travels forward. This stretches the waves out, which lowers the pitch. The exact same principle applies to light. If a source of light is moving toward you, its waves get compressed, shifting the light toward the blue end of the spectrum, what astronomers call a blue shift. If the source is moving away from you, its waves get stretched, shifting the light toward the red end of the spectrum, a redshift. And what Slipher had found, and what Hubble confirmed across dozens of galaxies, was that almost every single galaxy in the sky was redshifted. Almost every galaxy was moving away from us. But Hubble noticed something even more striking when he started plotting the data. It wasn't just that galaxies were moving away. It was that the further away a galaxy was, the faster it was moving. Every additional unit of distance came with an additional increment of speed. The relationship was consistent, measurable, and deeply strange. What this told him, what it could only mean, was that the universe itself was expanding. Not that galaxies were flying through a fixed space like shrapnel from an explosion, not that there was some central point everything was moving away from, but that the space between galaxies was growing, stretching, that the fabric of the universe was inflating in all directions simultaneously, carrying everything along with it like dots drawn on the surface of a balloon being blown up. This was not a minor update to the scientific worldview. This was the complete dismantling of it. The static universe was dead. And that took Einstein's cosmological constant, that correction he had introduced specifically to hold the static universe together, and flipped it entirely on its head. Because if the universe isn't static, if it's expanding, then you don't need the constant to maintain a balance. You need it to explain the expansion itself. And not just the expansion, but the rate of that expansion, which, as observations over the following decades would confirm, was not slowing down. It was speeding up. The universe is not just getting bigger. It is getting bigger, faster, and faster over time. The expansion is accelerating. And the force driving that acceleration, the energy embedded in the vacuum of space, the repulsive pressure pushing everything outward, is what we now call dark energy. Dark energy is not dark in the sense of being sinister or unknowable. It's dark in the sense that we cannot directly see it or measure it the way we can measure ordinary matter or light. What we can measure is its effect. We can observe that galaxies are being pushed apart at an accelerating rate. We can calculate how much energy would need to be present in empty space to produce that acceleration. And what we find is staggering. Approximately 68% of everything in the universe is dark energy. The vacuum of space is not empty. It is full of this outward pushing force, and the more space there is, the more dark energy there is to push things apart. This creates a feedback loop with no natural ceiling. The more space expands, the more dark energy is generated. The more dark energy is generated, the faster space expands. And crucially, there is no mechanism we have discovered that slows it down, which means that galaxies that are currently close enough for us to observe will, over vast timescales, eventually be pushed so far away that their light can no longer reach us. The observable universe will, in the very long run, become smaller and lonelier as the acceleration carries everything beyond our horizon. Einstein inserted a mathematical correction to preserve a universe he believed in. The universe he actually lived in turned out to be stranger, more dynamic, and far more unsettling than anything he had imagined. And the correction he invented to paper over his discomfort ended up being the key to understanding the most dominant force in existence. Which brings us back to the original question, the one we ended. Chapter 1. Einstein established that no physical object can travel through space faster than light, and that rule still holds, but it applies to objects moving through space. It says nothing about the expansion of space itself. Space doesn't move through space. Space simply grows. And it turns out that the growth of space, the expansion of the universe, can proceed at any speed whatsoever, including speeds far exceeding the speed of light. The light from the Big Bang did not travel 46.5 billion light-years in 13.8 billion years. The light traveled at the speed of light. It was the space it was traveling through that expanded, carrying the source of that light, and the destination further and further apart as the journey continued. The distance grew while the light was in transit, and with dark energy accelerating that growth, the gap between where light starts and where it ends up continues to widen with every moment. This is what the universe actually looks like. Not a static sea of stars, not an explosion spreading outward from a single point, but a fabric, an expanding, accelerating, dark energy-driven fabric that has been stretching since the very beginning and shows no sign of stopping. And that brings us, finally, to the beginning itself. So let's talk about the Big Bang. Not the version you learned in school, not the cosmic egg, not the single point of infinite density, not the great explosion that sent matter hurtling outward through empty space like shrapnel from a bomb. That version is clean. It is easy to picture. It fits neatly into a diagram on a classroom wall, and it is, in almost every meaningful way, a misrepresentation of what actually happened. The real story is harder to visualize. It is more disorienting. It asks you to let go of some very deeply held intuitions about how space and time work, and to sit with an idea that cannot be fully captured by any image or analogy. But it is also far more extraordinary than the simplified version. And once you actually understand it, once you feel the full weight of what the evidence is telling us, the universe becomes something genuinely different than it was before you knew. So let's start with the thing that almost everyone gets wrong first. The idea that the Big Bang happened at a specific location. When most people hear the word explosion, they picture a center point, a place where the detonation occurred. And they picture matter flying outward from that center in all directions, which means there would be an inside and an outside, a place where the explosion happened and a surrounding space into which the debris expanded. That is not what the Big Bang was. Here is the single most clarifying piece of evidence we have. The cosmic microwave background, that ancient wall of first light we discussed in Chapter 1, surrounds us in a perfect sphere. It does not appear brighter in one direction and dimmer in another. It does not have a center point somewhere off in a particular corner of the sky. It is, to an extraordinary degree of precision, uniform in all directions. Wherever you point your instruments, the edge is the same distance away. If the universe had expanded from a single point, the way a conventional explosion works, then the oldest light in the universe would not surround us evenly. There would be a direction, that way, pointing toward where it all began. There isn't. The beginning was not a point in space. The beginning was everywhere, all at once. The Big Bang did not happen at a location. It happened to everything simultaneously. The entire universe, whatever size it was at that moment, and we'll get to that, underwent a sudden, extraordinary expansion, not from one place outward, but at every point within it, all at the same time. Every location in the universe was the center of the Big Bang, because every location in the universe was the Big Bang. Now, that raises an obvious question. If the expansion didn't start at a single point, what did it start from? What was the universe like before the expansion began? And this is where we have to be honest about the limits of what we know. The straightforward answer that cosmology gives us is that the universe began in a state of almost incomprehensible density and temperature, not a single point, but a condition that existed everywhere. Every location that currently exists in the universe, every cubic inch of space that you can observe in any direction, was compressed into a state so hot and so dense that the physics we use to describe matter and energy today simply breaks down. Our equations stop working. Our models produce infinities and nonsense. We do not have a theory that successfully describes the universe at the very first instant of its existence. What we do have is a description of what happened in the moments immediately after that first instant, and that description is one of the most well-tested and precisely verified frameworks in all of science. In the very first fraction of a second after the Big Bang, the universe underwent a period of expansion so violent and so rapid that it makes everything that came after look almost gentle by comparison. This period is called cosmic inflation, and it is one of the most mind-bending ideas in modern cosmology. During inflation, the universe did not expand the way it expands today, gradually, driven by the steady pressure of dark energy. It expanded at a rate that was, for all practical purposes, instantaneous. In an interval of time so small that it defies any meaningful comparison, a tiny fraction of the first second of existence, the universe grew from whatever its initial size was to something enormously, almost unimaginably larger. Here is the analogy that the transcript offers, and it is a good one. Imagine a grain of sand. Now imagine that grain of sand expanding to the size of an entire galaxy, not over millions of years, but in an instant. Now take a sandbox full of grains, billions of them, and imagine every single one doing that simultaneously. Every grain, every point in that sandbox, exploding outward to galactic size all at once. That is one small, inadequate step toward grasping what inflation looked like. And even that is nowhere near the actual scale. But here is what makes inflation so important beyond just its sheer dramatic scale. It explains something that had been deeply puzzling about the universe for decades. The fact that the cosmic microwave background is so uniform, so consistent, so remarkably similar in temperature across the entire sky, in every direction, even between regions of space that, according to conventional physics, could never have been in contact with each other. Think about it this way. If you have two regions of space on opposite sides of the observable universe separated by 93 billion light-years, there is no mechanism by which they could have ever communicated with each other or influenced each other's temperature. Light from one side simply hasn't had enough time to reach the other, not in the entire history of the universe. So, why do they have almost exactly the same temperature? Why does the CMB look the same in every direction? The answer that inflation provides is that those regions were not always far apart. Before inflation, before that explosive period of growth, everything that would become the observable universe was crammed into a space so small that all of it was in contact. All of it had time to reach thermal equilibrium to settle into the same temperature, the same density, the same fundamental conditions. And then inflation happened, and all of that uniformly distributed material was stretched outward to cosmic scales, carrying that uniformity with it. Inflation essentially ironed the universe flat and smooth. And the extraordinary uniformity of the CMB is, in a very real sense, the fingerprint of that process. But inflation didn't iron everything perfectly, and that imperfection is the reason you exist. When you look at the CMB heat map, the image we described in Chapter 1, the blue and yellow map showing tiny temperature variations across the sky, what you are looking at are the remnants of quantum fluctuations. tiny random variations in energy density that existed at the quantum level before and during inflation, and that were then blown up to cosmic scales by the expansion. These fluctuations were the seeds, the initial unevenness from which everything that exists today eventually grew. Where the density was slightly higher, gravity was slightly stronger. Over time, that extra gravitational pull drew in more material. The denser regions got denser. Gas began to collapse. Stars ignited. Galaxies formed. Clusters of galaxies assembled along the threads of higher density, surrounding vast, emptier regions, the cosmic voids, just as the CMB predicted they would. Look at a large-scale map of the universe and you will see a structure that astronomers call the cosmic web, an intricate network of filaments and nodes and voids that bears a striking resemblance, at the largest scales, to the pattern of a human brain's neural network. This is not a coincidence in any mystical sense. It is simply what happens when gravity acts on a slightly uneven distribution of matter over billions of years. The pattern was already written into the universe in its first fraction of a second. All of that, every galaxy, every star, every planet, every living thing, traced back to quantum noise at the dawn of time, magnified by inflation into the architecture of the cosmos. Now, let's talk about what the universe was actually made of in those first moments. Because right after inflation, the universe was not filled with stars and galaxies and planets. It was not even filled with atoms. It was filled with something far more fundamental, a hot, dense, rapidly expanding plasma of energy and subatomic particles, colliding and interacting at temperatures that no physical object in today's universe comes anywhere close to reaching. In those first seconds, the universe was so hot that matter and antimatter were being continuously created and annihilated particles of matter, flashing into existence and immediately colliding with their antimatter counterparts and converting back into pure energy over and over again in a relentless churning cycle. For reasons that physics still does not fully understand, matter and antimatter were not produced in perfectly equal quantities. For every billion antimatter particles, there were approximately 1,000,000,001 matter particles. That tiny asymmetry, one extra particle per billion, is the reason anything exists today. When the universe cooled enough that particle-antiparticle creation stopped, the antimatter and the vast majority of the matter annihilated each other in a universe-wide cancellation. What was left over, that 1 in a billion surplus, became everything. Every atom in every star. Every molecule in every living cell, every photon of light that has ever illuminated anything. You are the leftover from an almost perfect annihilation. In the first 3 minutes after the Big Bang, an almost insultingly short window of time given what it produced, the conditions were right for nuclear fusion to begin. Protons and neutrons, the building blocks of atomic nuclei, began combining under the extreme heat and pressure. Hydrogen nuclei single protons formed first, the simplest possible atomic nucleus. Then some of them fused into helium and a small amount of lithium. After about 3 minutes, the universe had cooled just enough that fusion became difficult, and the process largely stopped. For the next 380,000 years, the universe existed as an opaque fog, a dense plasma of nuclei and electrons, so hot and so tightly packed that light could not travel freely through it. Photons were constantly absorbed and re-emitted, trapped inside the plasma, unable to escape. The universe, despite being full of energy, was effectively dark in the sense that no light could travel any meaningful distance through it. And then, at around 380,000 years after the Big Bang, something changed. The universe had expanded and cooled enough that electrons, which had been flying freely through the plasma, could finally slow down enough to be captured by atomic nuclei. Atoms formed for the first time, hydrogen and helium atoms, mostly. Simple, stable, neutral. And when that happened, when matter became neutral, the universe became transparent. The fog lifted. Photons that had been trapped, bouncing around inside the plasma for 380,000 years, were suddenly free to travel through space unimpeded. They streamed outward in all directions, carrying with them a snapshot of the universe at that exact moment, the temperature, the density, the distribution of matter at the instant the fog cleared. That is the light we measure as the cosmic microwave background. That is what sits at the edge of our observable universe. The CMB is not the light from the Big Bang itself. It is the light from the moment the universe first became transparent, the first light that was ever able to travel freely through space. And it has been traveling ever since for 13.8 billion years, stretched by the expansion of the universe from visible light all the way down into microwaves, arriving at us from every direction simultaneously, carrying that ancient snapshot of the universe's earliest legible moment. It is, in a very real sense, a photograph of the infant universe, and everything that came after the first stars, the first galaxies, the generations of stellar birth and death that forged the heavy elements, the formation of our solar system, the emergence of life on a small rocky planet orbiting an unremarkable star. All of it grew from the information encoded in that photograph. The universe did not begin with a bang. It began with everything, everywhere, all at once. And then, over 13.8 billion years, it arranged itself through gravity and nuclear physics and chemistry and time into the extraordinary complexity you see when you look at the night sky or when you look in the mirror. We have established that the universe began everywhere at once, that it has been expanding ever since, and that the expansion is accelerating. We have traced the story from the first fraction of a second all the way to the moment the universe became transparent and released its first freely traveling light. We have accounted for the hydrogen, the helium, the seeds of cosmic structure embedded in quantum fluctuations, the blueprint written into the CMB. Now the universe has to actually build something, because what we have described so far is raw material and initial conditions. What came next, the process by which a nearly uniform fog of hydrogen and helium became the staggeringly complex, structured, breathtakingly vast cosmos we observe today, is a story that spans billions of years and involves forces and substances that, frankly, we still do not fully understand. And the first thing we need to confront before we can tell that story honestly is this: most of the universe is missing. Not missing in the sense that it was there and we lost track of it. Missing in the sense that when we add up all the matter, we can see every star, every galaxy, every cloud of gas, every planet, every particle that interacts with light in any way that our instruments can detect. We get a number that is nowhere near large enough to explain what we observe. The universe we can see does not have nearly enough mass to account for the gravitational behavior of the universe we measure. Something else is out there. Something that has mass. Something that exerts gravitational pull. Something that played an absolutely critical role in shaping every structure in the cosmos. And something that, as far as we can tell, does not interact with light in any way whatsoever. It does not emit it, absorb it, or reflect it. It is, to every instrument we have ever built, completely and utterly invisible. We call it dark matter. And before you dismiss that as a placeholder name for ignorance, before you assume that dark matter is just a gap in our knowledge dressed up in scientific language, it is worth understanding exactly how we know it is there. Because the evidence is not subtle, it is not a single anomalous measurement that could be explained away. It comes from multiple independent lines of observation, all pointing to the same conclusion, all converging on the same invisible component of the universe. The first major clue came from galaxies themselves. When you look at a spiral galaxy, the kind with those elegant sweeping arms curving outward from a bright central hub, the expectation, based on Newtonian gravity, is straightforward. The stars at the outer edges of the galaxy, far from the dense concentration of mass at the center, should be moving relatively slowly, just as the outer planets in our solar system, Neptune, Uranus, move much more slowly in their orbits than the inner planets like Mercury and Venus. The outer stars of a galaxy should be orbiting the galactic center at a gentler pace than the stars closer in. That is what the math predicts. That is what should happen if the only mass in a galaxy is the mass we can see. That is not what we observe. When astronomers measure the actual rotational velocities of stars at different distances from the center of a galaxy, the so-called galaxy rotation curve, what they find is that the outer stars are moving far too fast. Not slightly too fast. Not a marginal discrepancy that could be brushed aside. They are moving so fast that, by conventional physics, they should not be in the galaxy at all. The gravity produced by the visible matter is not strong enough to hold them in orbit at those speeds. They should have flown off into intergalactic space long ago, but they haven't. They are still there, orbiting at these impossibly high velocities, as though they are being held in place by a gravitational field far stronger than the visible mass of the galaxy can produce. The explanation that fits the data is that each galaxy is embedded in a vast halo of invisible mass dark matter that extends far beyond the visible disk of stars and provides the additional gravitational scaffolding needed to keep those outer stars in orbit. The dark matter halo is enormous. It dwarfs the visible galaxy. The stars and gas that we can actually see represent only the luminous core of a much larger gravitational structure. And this is not just a feature of individual galaxies. It shows up at every scale we look. Galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or thousands of individual galaxies, contain far more mass than their visible galaxies can account for. We know this through a technique called gravitational lensing. Einstein's general relativity tells us that mass curves space, and that light traveling through curved space follows a curved path. This means that a massive object, a galaxy cluster, for instance, will act like a lens, bending the light from objects behind it and producing distorted, stretched, or multiplied images of those background sources. By measuring the degree of that lensing, by calculating how much the light is being bent, astronomers can work out how much mass must be present to produce that effect. And in every case, the mass calculated from the lensing is far greater than the mass accounted for by the visible galaxies in the cluster, typically 5 to 6 times greater. The invisible mass, the dark matter, outweighs the visible matter by a factor of roughly 5 to 1, consistently, across cluster after cluster after cluster. Whatever dark matter is, there is a lot of it. Approximately 27% of the total energy content of the universe is dark matter. Add that to the 68% that is dark energy, and you are left with just 5% for everything else. Everything we have ever seen. Every atom in every star, in every galaxy in the observable universe. Every planet, every person, every instrument we have ever built to study the cosmos. All of it, every single thing made of ordinary matter, accounts for just 5% of what exists. 95% of the universe is something other than what we can see or directly measure. That is not a comfortable fact, but it is the fact. Now, here is what makes dark matter even more fascinating than its sheer abundance. It was not just a passive bystander in the formation of cosmic structure, it was the architect. Remember those quantum fluctuations, those tiny seeds of unevenness that inflation stretched to cosmic scales, that we can see preserved in the CMB? After inflation, after the plasma era, after the universe became transparent and released the CMB, those fluctuations needed to grow. The slightly denser regions needed to pull in more matter, to collapse under gravity, to eventually form the galaxies and clusters we see today. But there was a problem. Ordinary matter, the hydrogen and helium that made up the visible universe, was still coupled to radiation in those early epochs. The pressure of light was constantly pushing outward against the inward pull of gravity. preventing ordinary matter from clumping together efficiently. If the universe had contained only ordinary matter, the gravitational seeds from inflation might not have had enough time to grow into the structures we observe. The universe might have ended up far more uniform, far more featureless than the one we actually live in. Dark matter changed that calculation entirely. Because dark matter does not interact with radiation, it does not feel the pressure of light pushing back against it. From the very beginning, dark matter was free to respond purely to gravity, free to start clumping, collapsing, building structure, entirely unimpeded by the radiation that was holding ordinary matter back. So while ordinary matter was still being pushed around by the pressure of light, dark matter was already assembling itself into the gravitational scaffolding of the future universe. It was forming halos, filaments, nodes, an invisible framework that ordinary matter would later fall into, like water flowing into channels already carved into rock. By the time ordinary matter finally decoupled from radiation, by the time the fog lifted at 380,000 years, and matter was free to move under gravity, the dark matter framework was already partially assembled and waiting. Ordinary matter fell into the gravitational wells that dark matter had already created, accelerating the collapse of gas clouds into the first stars and galaxies, filling in the structure that dark matter had already sketched out. Dark matter didn't just participate in building the universe. It drew the blueprints first. The result of this process, playing out over hundreds of millions and then billions of years, is the large-scale structure of the universe as it exists today. And that structure is one of the most visually and intellectually stunning things that science has ever revealed. If you could zoom out far enough to see not individual galaxies, but the universe on its grandest scales, what you would find is not a random scattering of matter through space. What you would find is a vast, intricate, three-dimensional web. Astronomers call it the cosmic web, and it is one of the defining features of the observable universe. The cosmic web consists of three basic structural elements. First, there are filaments, long, thread-like structures of matter, dark and luminous, that stretch across hundreds of millions of light years, connecting regions of higher density like cables strung between towers. Second, at the intersections of those filaments, there are nodes, the densest concentrations of matter in the universe, where galaxy clusters and superclusters assemble, where thousands of galaxies orbit each other in gravitationally bound communities. And third, between the filaments and nodes, there are voids, enormous, largely empty regions of space, hundreds of millions of light years across, where the density of matter is far below the cosmic average, and very few galaxies are found. The pattern, when you see it mapped out in 3 dimensions, is unmistakable. Filaments running through space like threads in a fabric, bright nodes at their intersections, dark voids in between. It looks, to an almost eerie degree of precision, like a neural network, like the microscopic structure of a human brain, scaled up to the size of the observable universe. This is not a coincidence, rooted in any deep connection between brains and cosmos. It is simply the geometry that emerges from gravity, acting on a slightly uneven distribution of matter over very long timescales. The mathematics of network formation, whether in neurons or in galaxies, tends to produce similar patterns. But it is a striking reminder of how the same physical principles can manifest at wildly different scales. And within the nodes of this web, within those dense intersections where gravity has drawn together the greatest concentrations of matter, the most dramatic events in cosmic history have played out. Galaxies have formed, evolved, collided, and merged. Supermassive black holes have grown at galactic centers, consuming matter and releasing jets of energy that can outshine entire galaxies. Stars have been born, burned through their fuel, exploded as supernovae, and seeded the surrounding space with the heavier elements that those explosions forged: the carbon, the oxygen, the iron, the silicon, the calcium, the elements that would eventually find their way into planets, into oceans, into living things. Every atom in your body heavier than hydrogen was forged in the interior of a star that no longer exists and released into space when that star died. You are, in the most literal sense, made of stellar debris. The calcium in your bones, the iron in your blood, the oxygen in every breath, all of it was processed through the nuclear furnace of a star, scattered by its death, and eventually incorporated into the molecular cloud that collapsed to form our solar system. The universe did not just create the conditions for life. It manufactured the ingredients, star by star, explosion by explosion, over billions of years, and then delivered them to the right place at the right time. And that brings us to a question that sits at the very edge of what we currently understand. We know the universe is expanding. We know that expansion is accelerating, driven by dark energy. We know that the large-scale structure we see today, the cosmic web, the galaxy clusters, the filaments and voids, was shaped by the invisible hand of dark matter, acting on seeds laid down by inflation in the first fraction of a second. But what is the universe ultimately heading toward? What does all of this expansion and acceleration lead to, in the end? That is a question that takes us somewhere genuinely unsettling. We have traveled a long way together. We started by looking up at the night sky and asking a simple question: why is it dark? And that question pulled us, thread by thread, into the deep structure of reality. The darkness is not emptiness. It is a boundary. And everything we have explored, the expanding universe, the ancient light, the invisible architecture of dark matter, the quantum seeds of cosmic structure, all of it points toward one final, unavoidable truth. The universe has a destination, and it is not a comfortable one. Based on everything we currently understand, the universe is moving slowly and inevitably toward a state of absolute stillness. Cosmologists call it the heat death, and it is, by any measure, the most complete ending imaginable. Here is how it unfolds. Stars are not eternal. Every star burning in the sky today is spending down a finite reserve of nuclear fuel. The smallest, most efficient stars can burn for trillions of years, but even they go out eventually. One by one, across timescales that make the current age of the universe look trivial, every star in every galaxy will exhaust its fuel and die. The last star will go out somewhere around 100 trillion years from now. After that, no more starlight, no more warmth, no more new elements forged in stellar furnaces. What remains will be black holes slowly consuming the last remnants of matter, dominating a cold and dark cosmos for an almost incomprehensible stretch of time. But even black holes do not last forever. Stephen Hawking showed that they very slowly radiate away their mass through a quantum process at their edges. Given enough time, even the largest black hole in the universe will evaporate completely and vanish. After that, nothing. An unimaginably vast, cold, featureless expanse of space. No structure, no complexity, no energy left to drive any process or sustain any organization. The universe reaches thermodynamic equilibrium maximum entropy and stays there forever. That is the heat death. Not a dramatic explosion, not a collapse, just a long, quiet, absolute, fading into perfect stillness. Now take a breath, because here is what matters. You are alive right now. Not in the cold, dark aftermath. Not drifting through an empty void. You are here during the stelliferous era, the age of stars, the brief, blazing window of cosmic history when matter is complex enough to sustain fusion, build planets, and generate life. And on one small planet, around one average star, the universe has produced something capable of looking back at all of this and understanding it. We are not just inhabitants of the universe. We are the mechanism by which the universe examines itself. The atoms in your brain were forged in dying stars. They are ancient, they are cosmic, and they have arranged themselves through 4 billion years of biological evolution into something that can ask where it all came from. The universe is 93 billion light-years across. It contains 2 trillion galaxies. It has been running for 13.8 billion years. And yet the most extraordinary thing we know of inside it is not its size. It is the awareness. It is the fact that something inside this vast, mostly empty, mostly dark cosmos looked up and started asking questions. The darkness at the edge of the universe is not an ending. It is a frame. And inside that frame, right now, the universe is awake. That is the story of everything.